and now let's look at, what we said we were going to try to accomplish in this course. Okay, so we said we're going to start by trying to figure out what is learning. Okay, what is learning? Let's try to pin down learning, and we pinned it down. Learning is outputting a final hypothesis G that approximates F. It's how successful are you in driving forward? And I don't care about anything that happened, in your past. I don't care about in-sample error. I don't care about, how you fit it. Did you fit it well? I don't care. The only thing that matters is the bottom line. Can you approximate F on new data? Okay. Now, of course, we have some, resources to do this, okay? And the most precious of those resources is the data. So we can try to learn on the data, but at the end of the day, we say we have learned if and only if your final hypothesis approximates G. And then that raised the very interesting question of, is this even feasible? Okay? How is it possible for a finite data set to be able to pin down in any way whatsoever what F is doing outside the data? So how is it possible that in any way whatsoever, what I see in my rearview mirror can help me at all in navigating the forward path, okay, in driving forward, okay? And that's where we had to sort of move into the probabilistic world, and we had to give up for sure. And then we reduced the problem to this two-step process where, in giving up for sure, what we were able to do was with high probability reach from inside the data to outside the data, and sort of ensure that with high probability, unless we're very, very, very unlucky, what we see in sample approximates what's happening out of sample. Okay, and that led to this, this two-step learning where, so the goal is to ensure that ability to reach from in-sample to out-sample holds, okay, and then go and look and see how well are you doing in-sample. Okay, and if you're doing well in-sample, you succeeded. If you're not, you fail. So the possibility to fail in a machine learning problem is absolutely fundamental. Okay, you have to be able to fail. Otherwise, it's just not possible to succeed. Okay, and how do we sort of ensure this first step of learning? Well, you have to use a simple hypothesis set, okay, one with finite VC dimension. So we did this beautiful theory which sort of analyzed hypothesis sets from the viewpoint of data, and we extracted this fundamental parameter of a hypothesis set that captures its complexity, the VC dimension. Okay, and so this choosing a simple hypothesis set and having a large number of data points, that's how we control the first step of learning, that E in is close to E out. And then, we now need to be able to find the hypothesis in this hypothesis set that's good. Okay, so that means we need a good algorithm for picking. Okay, so we need to be able to efficiently search the hypothesis set and get E in close to 0, and we discussed algorithms for doing this. And also it must be the case that some hypothesis in this hypothesis set has a small in-sample error. In other words, the hypothesis set you have chosen is good, and this is where picking good features and thinking about the problem are inescapable. Okay, you have to think about the problem, you have to pick good features and so on and so forth. In other words, you have to specify your hypothesis set before you see the data if you want to accomplish the first step, and then that hypothesis set, you try as much as you can to ensure that you have captured the right features and it can represent F, in which case you can get in-sample error small. Okay, now concretely, how do we do it? We discussed the linear model, man, and that's a bingo model. Okay, because A, it automatically accomplishes the first step of learning because it's a simple hypothesis set with a very small VC dimension, especially in low dimensional spaces. Okay? And, so you've got E in close to E out, and then we have algorithms, to sort of find the best hypothesis depending on whether you're doing classification, regression, or logistic regression. Okay? And it forces you to sit down and think about the problem and ask yourself, what are the right features? And I'm willing to maintain the argument that if you cannot more or less solve your problem with linear models, you have not quite understood the problem. Okay? You're not using, everything at your disposal in order to sort of understand the problem, get good features, and then use the linear model to solve it. Now, if the features you have gotten are, basically the right features, but, you need a little bit more flexibility in terms of a little bit more nonlinearity. Well, we showed you the nonlinear feature transform, which is this very powerful beast. Okay. Now, later on, we will study other models, for example, neural networks which cascade linear models. So the linear model is not only powerful and good on its own, it is the foundation for other more complicated models. And these other more complicated models attempt to sort of do some kind of automatic, feature construction, and then use the linear model. So you cascade linear models, okay, and in this way you can sort of maybe develop novel features, let's say, and then combine them in a linear model. So, but at the end of the day, we need to fundamentally understand the linear model and its capabilities. Okay. So that more or less is what is learning, can we do it, and how do we do it? But then, what separates the professional from the amateur is how to do it well. How do you control overfitting? Because there is always noise in the data. There is always noise in the data. Stochastic noise, deterministic noise. Okay. And so, overfitting is just an inescapable disease. You have to deal with it. Okay. And we discussed sort of two cures: regularization, which breaks the learning algorithm, puts a leash on the learning algorithm, prevents you, explicitly tries to prevent you from fitting the noise. And then validation is a sort of a reality check, a sneak peek at the out of sample error, where if you're sort of minimizing your error or doing model selection and you think you're getting better and better in sample error, but validation can come and say, hold on a minute, buddy, you might be looking at a better and better in sample error, but the validation error is not looking good. So this peak at the out of sample error is telling you you're starting to overfit. Okay. And at the end, we summarized all these all these foundations into sort of general principles. Basically, Occam's razor, sampling bias, and data snooping. Simple hypothesis. Make sure that the data is generated to satisfy the requirements of the theory, which is IID, and the training and test data must be generated from the same distribution. And data snooping, which basically says that you have to fix the most common type of data snooping is not fixing your hypothesis set before you look at the data. You have to fix your hypothesis set before you look at the data. And there are many ways in which data snooping occurs, in very subtle and non-contemporaneous, manners, with someone doing some research 10 years ago, and then you building on it. Well, you have in some sense data snooped because you chose your hypothesis on the basis of what was done 10 years ago. Okay, so that's the theory. Those are the foundations, and we will never be able to escape the foundations. Okay, and so now we're going to move on to sort of more advanced techniques, let's say. And you might think, oh, okay, great, fancy, and so we're done with the theory. We will never be done with the theory. So in everything we discuss, we will see all the various facets of this theory: overfitting, simplicity of the hypothesis set, the two-step approach, and so on and so forth. We'll see all these facets of the foundations cropping in here and there in order to make, the machine learning go. And that's unavoidable. Okay, what we have said so far is unavoidable. We have to give up for sure. We're in this probabilistic realm where we have to ensure the two-step process, and that's all foundational, that's fundamental, and it doesn't matter whether you're using a very sophisticated technique or the simple linear models. So the foundations are going to be with us for the rest of the course. Okay, but we're now going to start talking about perhaps slightly more advanced techniques. And before I just mention exactly what we will be talking about, this is going to be a relatively short lecture. Let me show you the realm of machine learning, and it really is a jungle out there. It has just exploded into this humongous field.